Welcome to the course Evolution of the Earth and Life. Today we are going to talk about how the continents formed. So the time span that we are going to be focusing around would be Hadean and Archean, and we are talking about somewhere around 4.6 billion years ago till 2.5 billion years ago. Now the crust have formed in Hadean, but as we know that the pre-Archean crust and any idea about the pre-Archean crust primarily comes from investigating the Hadean detrital zircons. So we do not really have any rock record from Hadean. Now the question is, how can we know about anything about Hadean? Well, the primary point of information comes from those few detrital zircon grains, but we also learn a lot about what might have been the first phases of cooling down of the Earth from observing other planets, from the moon and the rocks that we find in other planets and the moon. Now we know that if we look at the moon and also the other rocky planets, we primarily find one particular type of rock, and that is basalt. Basalt is one of the most common type of rock that we find in the moon, in other planets, sometimes even in things which are meteoritic. So it's quite understandable that when we think about Hadean, where the temperature was quite high and the Earth was being impacted by multiple meteorite events, they probably disturbed the Earth in a regular fashion. But there were times when the temperature also cooled down, and that must have developed some degree of fractional crystallization from the melt. So our understanding of the cooling down process of the Earth tells us that during Hadean, the Earth was cooling down, but it was getting disturbed because of these impacts. There was these large impacts, some of the impacts even created other bodies such as moon, but there were smaller impacts too. And about these impacts, we know from the history of the moon and its craters. Because Earth and moon are pretty similar in terms of their spacing, it's not very hard to imagine that the Earth was also being impacted. Now, when we think about the overall molten Earth, it was quite understandable that even when the moon formed, the Earth was already separated, the core was separated, the heavy metals, they mostly went down, sank and developed this metal-rich core. But the crust and the mantle was slightly different story. So part of the upper layer was still molten, and when the first set of minerals start to crystallize from that, from this mix, from our understanding of igneous rocks, we know that the first minerals to crystallize would be olivine. As a result, if there were formation of rocks, it would be an olivine-rich rock. Now we know that these olivine-rich rocks are called peridotite, and these olivines can crystallize at a fairly high temperature, somewhere around 1200 degrees centigrade. In fact, if you think about just partial crystallization or fractional crystallization of olivine, at times that can start even at higher temperature. So these olivine crystals were forming out of the melt, but because they are quite heavy, they have a higher density, they must have been going down, sinking down from this magma ocean, if we can call it that. So once a substantial amount of peridotite was forming, which are olivine-rich rocks, they were settling down, and that layer is primarily what we call a mantle. but it's not really the crust that are forming at the beginning. So with time, we can imagine that there was already existing core and there would be a substantial amount of formation of the mantle which are rich in this peridotitic rock. But once all the peridotites are formed or a substantial amount of the peridotite forms and the temperature cools down with time, then the remaining material would be relatively rich in silica and the temperature is much lower than when the peridotite started to form. During this process where the temperature lowered down and also that the olivines are already gone out of the system or majority of the olivine was gone out of the magma because they have settled down, we will start seeing the development of the next phase of minerals. And those next phase is the phase of pyroxene. This is one mineral, and the other mineral which is very common is something called plagioclase feldspar. Now these form at fairly high temperature but lower temperature than olivine. And this is interesting because they form a rock called basalt, which is very common not only on the earth but also in all other planets within the inner terrestrial planet group. So what we know that this pyroxene and plagioclase feldspar, they can form this kind of a mafic igneous rock, and one example of that is basalt. Now basalts are the rocks when they are forming at the surface. If the magma which is coming up and crystallizing pyroxene and plagioclase feldspar at the very surface, then they will have very fine crystal size. Sometimes they might not even have long time to develop large crystals, and therefore it's going to be something which we call an extrusive igneous rock, a volcanic igneous rock with this composition. That's what we call a basalt. But there can be situation where the same composition doesn't end up at the surface and they basically solidify below the surface. Then they will have large crystals but with the same composition of pyroxene and plagioclase feldspar. In that case, they are called gabbro. So gabbro is basically the intrusive version of basalt. Now, based on our understanding of Bowen's reaction series and what was the temperature profile like during Hadean as the primitive earth was cooling down, we think that the first formation after peridotite was the basalt and gabbro, and they capped the entire earth or majority of the earth with a very thin layer. Because these basalts have lower density than peridotite, in some sense they were floating above the peridotite or floating on the peridotite. So that's the first formation of the crust. Clearly, this is something that we are talking about an oceanic crust because the basalts are primary composition of the oceanic crust. So although they are lighter compared to the peridotite, they are still not very light, but they can create somewhat of a relief and they can basically create topographies such as sea mounds. But at the beginning, this is what the earth was like, which was there was a well separated core, then there was a mantle which was rich in peridotite, and then there was a very thin crust primarily made up of basalt and gabbro, and we are still talking about an oceanic crust. But this oceanic crust was all over. However, this oceanic crust will not stay as it is for a very long time, as we will see. Now, if we think about plate tectonics, and we know that the oceanic crusts are constantly being recycled through the subduction zones. Now, this subduction process and complete development of plate tectonics, how it worked at the very beginning of the crust formation, we really do not know well. Probably it was not a fully formed plate tectonic cycle that we see today, but there was some level of convection in the mantle, and therefore there was some level of movement of these crusts too. But there was also the involvement of water, because some of these rocks also dehydrated and released some of the water vapor, and there was water from outside also in the form of comets. In presence of this water, as well as still a lower temperature with time, basalts can melt at lower temperature. So, we have learned that the temperature or the melting point of a rock depends on pressure, depends on temperature, and also depends on the amount of liquid, especially water. So, in presence of water, things can melt at a lower temperature. So, during Hadean, after the formation of this basaltic crust, what we could see is that the next possible scenario is the partial melting of those basaltic material at a very low temperature, and that low temperature is resulting because firstly there is some involvement of water, secondly the part of the basalt that can melt at low temperature are the ones which are basically somewhere around here. So, if we look at the lower end member of the Bowen's reaction series, we know that at lower temperature, if we start with a rock, the first things that are going to start go into the melt or partially melt are the ones which require lower temperature for crystallization. So, they are going to be the first ones to go into melt. So, with involvement of water and with the existing basaltic crust or basaltic magma, we will also see that part of it starts to melt again, and these melting would take preferentially the things from the lower part of the Bowen's reaction series. So, then we will see this difference that the rock is basalt, but the melt which is producing from it has a much higher component of silica in it, because it is primarily melting the lower part of the Bowen's reaction series, things which correspond to lower temperature. As a result, we will start seeing a development of a silica rich magma, which once cools down will form a rock which will primarily have quartz, which will also have some feldspar, but this feldspar is going to be different from the basaltic feldspar that we talked about. We will find potassium feldspar, and also among this plagioclase feldspar, there is one version, one N member of a solid solution in the plagioclase feldspar, which is sodium rich. So, we are going to get this sodium rich feldspar, potassium feldspar, quartz, sometimes a bit of mica, sometimes it could be a little bit of pyroxene, but primarily dominated by quartz, these two types of feldspar. And this is the composition of the rock called granite. And this granite is very different from any other planet, because we do not really see a lot of granites in other planets other than Earth. And this granite is substantially lower density compared to basalt. It is lower density from peridotite, but it is even lower density compared to basalts. As a result, when we are comparing basalts and granite, the granites are going to create high elevation compared to the basalts. So, now we have an Earth where there are basalts which are creating the relatively low elevation regions, which are capping the low elevation regions, and then there are these newly formed rocks which are much lighter and creating a highly highly elevated areas, and this is the formation of first continental crust. So, granite is the main composition of continental crust. Now, the question is, how do we even know about anything, whether the continental crust formed during Hadean or not? Well, one of the source of information are these detrital zircons. So, zircons are minerals, they are mineral grains, but sometimes these zircons also have quartz inside them, and these quartz, as we know, cannot form in very high temperature. They cannot even form in conditions where it is only basalt. So, therefore, people have taken it as a proof of development of crystallization at lower temperature and probably from a granitic development of a granitic crust. There are other geochemical evidences too, which points towards the development of these zircon minerals at lower temperature, probably in the presence of water. But unless we find the rocks, it is still difficult to constrain to all these points. But we do not get rocks from the Hadean time. The first time we start getting the rocks, it is from Archean, and as we said that we are basically drawing the boundary at 4 billion years. So, before 4 billion years we are calling it Hadean, and after 4 billion years or younger than 4 billion years we are calling it Archean, and the boundary is basically marked by the appearance of rocks. So, in this map you will see these gray regions, all these gray regions basically indicate Archean rocks, and these kind of very old rocks which indicates the old and stable part of the continental lithosphere are called cratons, and these cratons are found all over the world, including India, where we have Dharwar craton. But if you see all over the world, you will find that there are very, very old rocks. Some of them also contain zircon minerals, which are even older than the oldest of the rock record. So, at this point we understand that in Hadean we only have the mineral record, but that mineral record indicates probably there was development of both oceanic crust, water, as well as continental crust in Hadean. But when it comes to rock record, we start finding rock record from Archean onwards. So, and in the Archean record, we also find evidence of development of continental crust as well as some of the oceanic crust. And the ages range between somewhere around 4.4 billion years to 3.6 billion years, and some of the very old records are found from all over the world. But one question still remains, and that is, the continents that we talked about are only development in narrow patches. How do we find these large continents that we see today? And second point is, the continents that we were talking about were probably very small and thin. How do we get continents which are so thick today and so large today? So, that is the question that we will try to understand. So, we know that there are two major processes by which the continents can grow. One process is called magmatic addition. So, magmatic differentiation of low density silica rich rock in Earth's mantle and vertical transport of these kind of felsic material to the crust can develop the continental crust. The important points are this low density and silica rich rock, because that is what finally is going to create this granite. The second important point is that because they are low density, as we know, they are going to be buoyant, and therefore, they can actually rise up from the mantle and create this material which will finally become the continent. The second point or the second mechanism of growth of the continent is by the integration of crustal material previously differentiated from mantle material into existing continental masses by horizontal transport during plate movement, and this is called accretion. So, magmatic addition primarily talks about vertical movement and therefore development of some continental mass, whereas the accretion basically talks about something about the lateral movement of materials and then adding it to existing continental mass and therefore adding to the surface area of the continents. So, there can be different types of accretion that can happen, and we are going to see some of these examples. So, as I mentioned that in magmatic addition, magmatic differentiation can happen of low density silica rich rock. Now, most new continental crust is formed in subduction zones from magmas formed by fluid induced melting of the subducting lithospheric slab and mantle material above the slab. Now, if you recall that if we have an oceanic lithosphere and then another oceanic lithosphere, if this oceanic lithosphere is older, they tend to be relatively dense and compacted. Because of their higher density, they are going to go down. As they are going down, they are also carrying some of the water trapped in the sediments, but some of the hydrous minerals are also going to leave off this water. Both of them try to reduce the melting point of these rocks. So, as the rock is going down, it is experiencing higher temperature, but it is also the melting point lowers down because of the addition of water. As a result, they will start to melt, and as they start to melt, they will also have the buoyant magma going up. Now, because this to start with has a completely different composition than the peridotitic magma from which the oceanic crust primarily forms. This is already a basalt, already a differentiated one, and from there its further fractional crystallization and therefore further differentiating. Therefore, it is going to create things which will not be mafic in nature, it will be intermediate or more felsic. As a result, this one is going to create these kind of islands or island arcs, which are going to be really light in composition, felsic in composition, and that there are processes where you can keep it for some time and even further differentiate it to make produce felsic magma, and that can create a small continental part which will have this felsic composition, and they can as they reach the upper crust. So, that can be one possibility of magmatic addition which will create continental mass. Among the accretion, the first case that we are going to talk about is the buoyant fragment, accretion of a buoyant fragment. So, a crustal fragment that is too buoyant to be subducted may be transferred from a subducting plate to a continent of the overriding plate. Now, it can be a small piece of the continental crust or a thickened section of the oceanic crust, but anyway the moment this one is going down, this part cannot go down because of its low density, it will tend to go to this direction, but this will eventually go down, and this is basically going to be something like which is sticking to this existing continental part, but it is not going down and eventually be part of this existing continental part, and that is what we call accretion of the buoyant fragment. And by adding these kind of portions, a continent can eventually grow. Another type of accretion is the accretion of island arc. We just talked about it. So, when the island arcs are forming because of the subduction, there is a possibility where because this plate is moving in this direction and this plate is moving in this direction, the sea in between can eventually close up. As it is closing up, we are going to find these islands and the island arcs coming closer to this existing continent. And eventually this part will be part of this continent, it will be accreted, and all these accretions are basically involve enormous amount of pressure and melting, so that they are sutured, they are glued together with the existing continent. There can be accretion from along a transform fault. Accretion terrains can be transported laterally along the continental margin by transform faults. As we know that the transform faults are when the continents are passing along each other, or the plates are passing along each other, not closer to each other or far away from each other. So, in that case there is a possibility that there is a continental fragment on top of one plate and there is existing continent on the other plate. As this plate is laterally moving, they can come in contact with the continent and eventually get sutured up. So, in that case this continent will also grow. The last one is the accretion by continental collision and rifting. Now, two continents may collide and be sutured together and then break apart later at a different location. So, again let us take a collisional margin where two continents, this is continental plate A and this is continental plate B, and they are coming closer to each other. Now, because both of them are continental plates, they have a tendency not to subduct well and to sort of bounce back up. So, eventually this plate will be merged with this plate and create a larger continental plate, and they can break apart in different parts again and make different configuration. So, this can be another type of continental configuration change. But the continents do not stay as it is, they also modify, and one of the primary mechanisms of modification is through mountain building process. So, mountain building process is again the continental convergence, where it involves only the continental plates, and because continental crusts are much more buoyant than mantle, they the colliding continents resist being subducted, and therefore they sort of rise up, and as they rise up they go through folding as well as faulting. So, both of these are basically deformation of rocks, and they do not have to be exactly at the place where things are colliding. It can be stretched to hundreds of kilometers. So, hundreds of kilometers around this area can be deformed and develop a complete new architecture of the continental crust, and that is how the continental crust, which may have formed 4 billion years ago, modify through time. And this is one of the other ways of making the continents thicker. So, as things collide, as they buckle up, we also see underplating, and sometimes these continents can buckle up and create huge thicknesses, which are not very common when the first continents were forming. The thickness of the continents are primarily guided by the internal heat. So, with increasing heat, the crust gets thinner, and we know it because every place where there is a rifting, so in the intraplate volcanisms, wherever there is a rifting, wherever there is enough heat, the lithosphere gets thinner. And that also tells us that at the initial part of the Earth's history, because the Earth was really hot, the lithosphere must have been quite thin. The continental plates also where they were forming must have been thinner. As the temperature goes down, it gathers more mass and it becomes thicker. The second reason for change in the thickness of the continent is the rate of erosion. So, the question is that we have learnt all these processes by which the continents can grow in size, the continents can get thicker. Why do not we find really thick continental plates extending beyond a certain limit? The reason behind that is the erosion. So, the erosion basically reduces the thickness of the continental plates, and the erosion depends on what kind of rock it is made up of. The igneous and the metamorphic rocks basically have higher resistance towards erosion. On the other hand, if it is a sedimentary rocks, it is much easier to erode. The climate plays a role. So, altogether they are going to control how thick the continents are going to be. So, the continents may have been very thin at the beginning and also small at the beginning, but with time, through accretional process, through the process of magmatic addition, the continents grew in size. But it is not a single directional growth where with time it is only going to grow, because there are activation of plate tectonics, it will also get rifted and eventually get subducted as part of the process of plate tectonics. So, these riftings can also create break apart existing large continents into smaller fragments. The thickness of the continents are also going to change. At the beginning must have been a thinner continent, but with time, with the lack of temperature or loss of temperature, resulted into relatively thicker continents, but the erosion checks on the continental thickness. The erosion plays a negative role on the continental thickness. So, therefore, even with the orogenic processes, it makes the continents thicker, it eventually gets flattened out because of the erosional processes. So, in summary, today we learned what were the first rocks that formed on the earth, and how from forming the oceanic crust, we also started finding the continental crust on the earth. And why do we find such continental crusts on the earth and not so much on the other planets? We also learned what are the mechanisms of growing the continents in size. We also learned how the continents can become thicker with time, but how erosion can play a role to balance that in terms of maintaining a particular thickness of the continents. Finally, we learned that the development of the Hadean crust was primarily the development of oceanic crust and eventually forming the continental crust, but these are through the records of the zircon minerals. The first continental crust record and the oceanic crust record we are getting from the Archean rocks preserved. So, the appearance of rock marks the boundary between the Hadean and the Archean. So, here are some of the resources that I have used for this lecture, and here is a question for you to think about. Thank you.